Okay, so I am planning on writing a blog post series over Christmas, if I get round to it, called 12 Monads of Christmas, which is, if I get round to it, a 12-part blog post series, one post per monad. And what I've done is I've taken the content that I had in mind for that and squished it into an hour. So it'll be probably a little bit fast and a little bit disjointed, and suddenly it'll be, this is day 2, and I'll just change topic. Okay, and then after an hour I'm going to stop. I'm not going to force you through the whole thing. So the days are themed around specific monads, but I talk about other stuff around those monads. So a lot of them are also monad transformers, and so I'll be talking about a monad and suddenly I'll stick a lift.io print in there sometimes. Just accept that that means I am asserting there's a monad transformer that works. Okay, so here's a program. Does anyone recognize this language? 1, 2, yeah, 3. Okay, so this is a basic program. It's going to do 2 things. It's going to input a string and store it in a variable called $, and then it's going to output that string. Okay, and we can give this program to our basic interpreter on our ZX Spectrum, and it will read in a line and write it out. So that's the same thing in Haskell. We're going to read in a line, store it in a variable called v now instead of $, and then we're going to output it. Okay, but main really is just, I can't really gesture here. From the Haskell perspective, what Haskell sees is not a sequence of instructions. What it sees is one more person. Welcome. Okay, so what it sees is just a single I/O value. So I/O unit, okay, that's constructed by that. And so you can do something like that. We've got main, and we've got all these expressions. I haven't actually checked that will compile, I just think it might. Okay, and that will do a thing. It will also read in a line and write it out. But this is just to emphasize that we can get our single value, what that is, I/O unit, however we want. We don't have to use do notation or monadic operators or whatever. Okay, so I sort of stick it in some structures and whatever. Okay. But if we go back to this do notation here, what that desugars to, so hopefully you all know you have do notation that gets sort of split up into a lower level piece of Haskell that looks like that. So we've got a get line, and then we've got this lambda expression which takes v to put str in a v. In the middle we've got an operator that joins them. Okay. And the thing that's in charge here is this bind operator. So arrow equals is bind. Okay, forget what one side's doing, forget what the other side's doing. The thing that's really in charge is bind, and that gets to decide what happens with the left or with the right. Okay, so you can look at it as do the first thing, which I've called first thing there, and then do the rest of the program. Okay. That's all I'm going to talk about for I/O at the moment. Okay, just think about a lot of the times there's do a thing and then do the whole of the rest of the program, joined together by this bind operator. So day 2, somehow I'll make a day's worth of post out of that. Day 2 is the list monad. Okay, here's a thing that will generate a list. So we've got x times y, where x comes from 1, 2, 3. And y comes from 10 and 100, and that's the output. It'll give us 10, 100, 20, 200, 30, 300. Okay, that looks completely different from this do form. Okay, but it is monadic. You can rearrange it, and you can write it as a do expression, just like that. And so we can desugar that a little bit, and we've got the first thing, and then we've got the rest of the program. Okay, so the first thing is pick something from 1, 2, 3. If we go back to here, we're saying the first thing we're going to do is pick a value of x from 1, 2, 3. Okay, and then the rest of the program is we'll take that value and do the other bit of the do expression. Okay. So there's this other formulation of monads which uses fmap and join, and so they're equivalent. It's equivalent if you use bind. You can also not use that. You can use join, and the syntax looks a bit different. So the syntax can look like this. We take the first bit of the program, so that first list, and we map the rest of the program over it. Okay, that's just a map on lists. And so we end up with this list here, where it's like if we, I've got a laser pointer, that doesn't work. It zooms out. Where were we? Here. Okay, so I'll use my mouse cursor. Okay, so what we're going to say is if we picked 1 and ran the rest of the program, we would get these results. Okay, so we've mapped from this 1 to here. If we picked 2 and ran the rest of the program, we would get these results. And if we picked 3 and ran the rest of the program, we'd get these results. Okay, and then join sticks them all together. So join for the list monad is concat. Takes a bunch of lists and adds all the elements together, and we get the same result here. And that's equivalent to this bind notation, where you can write 1 in terms of the others. So something that I then realised was I didn't really know what that join notation looked like if you used IO. So let's do this get line, put line thing again. We've got the first thing is doing a get line, and it's an IO action that's going to return a string. And then the rest of the program is going to take that string and output it. Okay, so that first program we had. And what we should be able to do is like we did on the previous slide. So here to run it, we map the rest of the program over the first thing, and then we join that together. So what happens if we map this rest of the program over our first thing, get line? So let's look at the types. This is a type IO string, and we're going to map in a thing that takes a string and gives us an IO unit. So that we replace this string with IO unit, and we get this IO action that's going to return another IO action. Okay. So I'm like, well, all right, that's going to give us an IO action, and we're going to get an IO action back, and we should probably run that. Okay, I wasn't really sure how that would actually play out in practice, but what we can do in here, maybe, let's see if I have hopefully I don't have anything incriminating in here. Hopefully, oh, there's a GHC prompt. Oh, that's as huge as it goes. No, I won't do that. So the hands-on demo, because my window's too small, I won't do, is we've got an executable thing here, and we can run it. What happens when we run it? When we run it, it does a get line, and then it returns another IO action. What's that IO action going to do? It's going to output what I entered to the get line. Okay, and I can run that second IO action as many times as I want. Okay, so maybe I will show it. Where in these many windows do I have that terminal? Here? Here, okay. So, fmap, put strlen, get line. Okay, that is IO. How far back, who cannot read this? Have you got it up on that screen there as well? Oh, okay, good. Yeah. Okay, so that's our type. If we run it, and let's keep the results, I'm going to write hello world, and we've now got back this X value. Okay, so that's a IO action as well. So I can run that, and it prints hello world, and I can run it lots of times if I want. Okay, So that's a slightly different presentation of what join looks like. Okay. So day 3 is maybe. Okay, we're all going through monads that I hope everyone's familiar with at the moment. So maybe is kind of like mini lists, and it's also a little bit like mini exceptions. And I'll go through what I think of those. Who knows what a natural transformation is? Who's tried to do any category theory in Haskell? Okay. So there are these 2 natural transformations called maybe to list and list to maybe. Those are just in data.list. They're just library functions. One goes from a maybe type to a list, and one goes from a list to a maybe. So list to maybe you can also think of as a safe head. So if I have an empty list, it's going to return nothing. If I have a multi-element list, it's going to return that first element. Okay. And a natural transformation is not just a function that has that type signature between, 2 monads or 2 functors in this case, but it also matches these rules here. So there's this diagram here. Going through lots of materials today. Wake up. Okay, look at my diagram. Okay, this is a commutative category diagram. So if we start in a list of integers at the top, we can convert that into a maybe integer. Okay, or we could start with a list of integers and we could map some kind of function across it using fmap. Okay, so we can map a list of integers to, say, a list of strings. Maybe we could use show or something like that. Okay, and then when we've got this list of strings, we can use the same list to maybe to go to a maybe string. Okay, so there's 2 ways we can do this diagram, and if this natural transformation obeys all the laws, it doesn't matter which way round we go, we're going to get the same value. Okay, so we could either convert to a list and then fmap, or we can fmap and convert to a list. And we can quick check that because we do Haskell, so we use quick check. So here's a law. We say if I take a list and I convert it to a maybe, and then I map some function over it, and I'm just using absolute value here as a function, that is going to be the same as if I take that list, map the function over it, and then go to a maybe. Okay, and you can run that. It just goes, yeah, works fine. Okay, I've lost the line here, but it also works if you start with a maybe value, convert it to a list and map a function, works the same that way. Okay, so both of those are natural transformations. They both obey this rule. Okay, that's cool. But that's, hello, that's just on functors. You need functors for monads, but monads have this extra bit of structure. Okay, and there's a thing quite like a natural transformation called a monad morphism, which is looks like this. Oops, it's going to go from some monad to another monad. So again, we've got maybe to list and list to maybe. Okay, are those going to be monad morphisms? So what are the rules for monad morphism? First, it needs to be a natural transformation. Then we need return to work. So if I return 7 in list, I get a list with just 7 in it. If I return 7 into maybe, I get maybe 7, and then I can convert that to a list. Okay, and it doesn't matter which way I do it. I can go straight to a structure, or I can go to the other structure and then transform down to it. I should get the same result. And I can quick check that, and it looks like this. So return x equals list to maybe return x. That works for both of them in this case. Okay. The other rule that monad morphisms have, which is this is the bit where you capture the difference between a list and a maybe, is if I am in one of the monads and I do some action like picking an element. Oh, sorry. There, okay, and then do another thing, so that's a sort of prototypical monad action, and then whatever comes out of this I take it into my other monad. That's the same as taking this action into the monad and then running it and taking this action into the monad. Okay, so again, it's sort of this commutative thing where it doesn't matter which way round you do things, it should give us the same results. I went to quick check that, and if you say maybe to list, that works 100 times at least. So I've used a little function like this. So I'm going to go from a value v and say I'm either going to return nothing or just a value. Okay, I couldn't use abs because that doesn't have the right monadic behavior. Okay, but it works going from maybe to a list. It doesn't work if you go from a list to a maybe. Okay, and the case that fails is the list 0, 5. So a list of 2 elements 0 and 5. Okay, so if I start with a list 0, 5. Where are my rules? Trapped in a twisty maze of scroll bars and multiple screens. Okay, so we've got this list 0, 5. If I pick an element 0, pick an element from the list, and then I run my test on it. The first time, if I pick 0, it doesn't pass my function, and it backtracks and tries 5. Okay, because list you've got backtracking. If I do that in the maybe monad, if I take 0, 5 to a maybe, I throw away that 5. So I've pruned the potential search tree. We'll only ever look at the 0 case, and I've lost that data. Okay. I think I need a diagram for that, but you're not going to get one. Okay. So what we've done by going from a list to a maybe is we've pruned off all the non-determinism. You can either, well, almost all the non-determinism. You can either have a value or you can fail to have a value. You can't have a choice of multiple values. Okay. So we ended up with these. Maybe to list is a monad morphism. List to maybe is not. Okay. So that's how you end up where I said this is like mini exceptions as well. You can either have a value or you can sort of fail and prune yourself, but you can't have multiple values. Okay, so day 4 of monads is this is 3 monads, but they sort of come together. These are, so we've had IO monads, which is like a doing monad that interacts with the world. We've had list and maybe, which are like containers that hold values. And then reader, writer, state are monads that wire together functions. So they're sort of saying, with state, take an output value from this function and stick it into the input of the next function, and sort of do this cookie cutter syntax, boilerplate, cookie cutter boilerplate. Okay. I'm not going to say much about that, but I did come across this law, which I quite like for characterizing what a reader monad is. So if we do a thing in a reader monad, and then we forget the value that it's, returned, and then we do another thing, we might as well have just done that second thing. Okay? You can't observe this M ever happening, because all it could have done is burn CPU time a little bit. Okay, it doesn't have any effect on the environment. So that seemed like an interesting way of characterizing reader monads, which I'll come back to later. Okay, so day 5 was going to be about how you can't make a set monad, and then I went Googling around and discovered that you can make a set monad. So I'll talk about why you can't make one first, and then I'll tell you roughly how you can make one after all. So if we have some fake notation, okay, this isn't Haskell, real Haskell, but you'll have to sort of imagine that this works as you might expect. So if we've got a set of integers, -1, -3, 3 and 7, and we're going to fmap the absolute value function over that, what are we going to get? We'll get 1, 3 and 7 in a set. Okay. Implicit in making that work, we needed equality. And in the Haskell implementation of set, they also need ORD, but you really only need equality to make that work. Okay, we had to be able to say, all right, I've got 3 and -3, but once I've F-mapped them, they're now the same value. And that's how we can end up with this smaller set. Okay, but what about if I want to F-map some other function? So I'm going to F-map const ID. That's going to give me a set of string to strings, for example, or something to something. Okay, to make that work, well, if you're like on paper doing your maths homework, you can say, well, it's always the ID function. So we'll end up with a single element set called ID. But in Haskell, we don't have any way of comparing functions. Okay, if you can't say ID equals ID, you'll get a type error. Okay, so F-map doesn't work, and so functors don't work, and for the same reason, bind doesn't work. Okay, we can somehow produce these sets of things that we can't compare, so we can't make them behave as a set. Okay. So that's why you can't make a set monad, or why you can't make one in the same way as you can make a list monad, because we need these equality constraints. So maybe we can put them somewhere else. And we can. What we can do is make this new data type. So this comes from set-monad on Hackage, and I've tweaked it a little bit, but we can make a new data type called set, and we have these 3 constructors for it. So this doesn't really look quite like you would imagine a set looks like. We've got prim, which says if we've got a data.set set, so a normal Haskell set with an ordering constraint, then we can just make one of these sets ourselves, sort of just lift it straight through. The other condition is if you have a single element, we can make that into a single element set. Okay? A single element set doesn't actually need these constraints, because we know it's only got one element. So there's no sort of equality on that, it's trivial. Okay, and then we've got this weird thing, bind, which looks a little bit like bind in monads. Okay, and that says if I've got a set and then a function from that type to other sets, we can come up with this other set. Okay, there's no ORD constraint on that. Okay. And we can build up what's essentially a syntax tree of binds, primitive sets, which have the order constraint. If I do a return, then I can end up with a singleton constraint, a singleton set that doesn't have the order constraint. And I end up with this big syntax tree. And then maybe I want to evaluate it. And what I can say is, if you want to evaluate one of these syntax trees, you can only do it to result in a set that has the right constraint. So I can make a syntax tree which is describing how to build a set of functions, for example, but I can't actually run this evaluator function on it to evaluate it. Okay? So you have 4 cases for evaluating this. If you try and evaluate a primitive set, that's a set. That's fine. That's pretty trivial. If it's a singleton value, we can use the set singleton thing, and we know that singleton will work because we know we've got the order constraint. And then there's 2 bind conditions. One is if we're binding a singleton set here, and one is if we're binding a regular set here. And the singleton one doesn't need any set operations, because if we're binding a single entry, we don't need any equality at that point. So that's this sort of interesting way of constructing a syntax tree and then saying, well, you can only construct sets this way with the right constraints on them. You can specify how they go to fit together, but you can only ask for an answer if you've got the right constraints on the evaluation function. Sorry. Okay. So if we were to say down here, run return ID, You could make a set structure with return ID in it, but if you tried to evaluate it, it would say, well, this isn't a set. A question from the audience.
Yeah, where's the equality gone?
Oh, sorry. So actually Haskell sets use ORD for the set equality, because you've got ORD has a value EQ, so we don't actually need that.
So ORD
implies equality, yeah.
Why can't I have bind? Yeah. Why can't I have the first argument bind being bind?
Oh, there, am I missing a case? Oh, I'm missing a case. You can. This is actually when I was stealing the source code out of Hackage earlier. There's it's also a Monad Plus instance, so there's about 15 different conditions where they really go into different paths of how this can work, and the way they avoid requiring ORD instances on everything is to write out the situations where you don't need it explicitly. So this thing has a lot of conditions, and apparently I've forgotten to copy one of them. Okay.
Sorry.
Yeah.
So, like in theory,
yeah.
If we have an enumerable type where we can enumerate all the values, we could, in theory, come up with an EQ or functions.
Yeah. So you could make your own. You could make your own run function that takes one of these. You could make your own run function which takes one of these set objects and has its own special way of evaluating it. Yeah. And that's basically what's happened, is the monad bit is this, and it's separate from the evaluator. Okay, day 6 is something different. Conduits. I think we've had a conduit or a pipes talk here before, maybe some years ago. Okay. Okay, so this is a monad that lets you stick together sort of coroutines that can pipe values. Excuse me. Out of a source, there's this pipe operator that says pipe your values through this conduit to a sink, and we'll get some result at the end of that sink. So here's a couple of code samples. So we've got a source. This is the first bit where I'm like, oh yeah, this is a transformer, by the way. So here we can output a message. We're going to yield a couple of values up our pipeline, and then we're going to yield all the integers from 100 to 200. So this is a bit of a monadic coroutine. Then we've got a sink, and all the sink is going to do is say, I'm starting up. It's going to await a value and then say, oh, this is the value I've got. Okay. So the two operations that we've got in the conduit monad are await, which makes us wait for a value from downstream, and yield, which sends a value upstream. And you can stick them together, source function attached to the sink function, and you run them. We see the sink starts up, and then it goes off to await a value. So now conduit says, all right, well, we'll go to our source and let this run, and the source will run until it yields a value, and it yields 1. We drop back down here and say we've got 1, and then that's the end of it. Okay. The rest of the source doesn't run. Okay. Once the sink is finished, that's it. So it's sort of, they are two routines running at the same time, but the one at the sink end of the pipeline is in charge. Okay. So we could stick a filter in. So I'm going to say a source, some filter, and a sink. And what that's going to do is say, all right, I'm waiting for some stuff. I'm waiting for a value. And then depending on what the value is, I'm going to do some things. So it might be that there's no more input, in which case await will give me back nothing. And I'll say I've reached the end of the stream. Or I might get back a value. And I say if I get back the value and it's more than 102, yield it upstream. yield it onto the sync, and then loop round again by calling some filter, so it keeps looping. And otherwise, so if I get a value but it's not greater than 102, just going to forget it and loop round again. So what this will do is sit looping round with fire values in one side, and what comes out the other side is only numbers bigger than 102. If they're less than 102, we'll discard them. So if we run it, scroll down, sync starts, the filter starts, the source starts, then the filter says, oh, I'm skipping value 1. Then the filter says I'm skipping value 2. Then the source says, all right, well, I've gone through my first bit of the source. Now I'm moving on to this bit where I enumerate the numbers 1 to 100. The filter says, all right, I'm skipping value 100, skipping 101. Oh, I'm going to pass on 102. Oh, actually passing on 103, sorry. And then the sync says, all right, I've got a number. We'll print it out and stop. Okay. So what this lets you do is write, if you're used to doing things in Unix pipes, for example, you can write in a style like that where you've got a coroutine that just runs and doesn't have to pay too much attention to what's happening with the output values. Okay. So you might look at things like lazy I/O or lazy list generation and things like that, and that's a classic Haskell approach to doing something like that. We have a function that generates an infinite list, and we feed it in, and the function generates an infinite list, and the consumer just consumes this list, and the pieces of code are separate. But that can lead to space leaks, for example, if you accidentally keep a reference to this list to the start of the list. And what Conduit is trying to do is say, well, we're only dealing with one value at a time, or a very constrained set of values, and then when we're done we can forget all of that. Okay, and you might be dealing with a lot of values at once, so you might make a gzip compressor, for example, that needs to pull in a bunch of data and maintain state and things like that. But you've got more control over where references to things are being kept, so you can do things in a bit more constant space. All right, day 7. We're going through the days. So day 7 is about Haskell, but I'm not going to talk about Haskell at all. So it's the one way of characterizing it is the reader monad when reads are very expensive. So by expensive, I mean maybe your data is very large. So in Haskell's case, imagine all of the data on Facebook, okay, is the data set they have access to. So you can't really do ask like you can in a reader and get it back in a Haskell value and then run some functions over that, which is what you would do in a reader monad. So that's a sort of stereotypical use of the reader monad. We'll get maybe our configuration file, and then we'll pull out a field out of that configuration file. If you imagine, all right, we're going to get everything in Facebook into RAM, and then we'll run a function over it. Okay, that doesn't really work. So we've got expensive reader, where we want to say, well, actually, here's a query that I want to go and be executed on some remote query engine, like a database, an SQL server. Facebook has various data sources that they use. And it starts to sound a little bit I/O-like, because you're saying, I want you to go and do this stuff, and then come back with a result. Very imperative sounding. But I'm going to say it's still reader-like, because in the specific case that you use Haskell for, you can only make queries. You can't make mutating changes. So this sort of reader rule that I had earlier applies. If I make a query to a database and then throw away the results and make another query to the database, I might as well have not made that first query. Okay, so that's different from if I format my hard drive and then print hello world. That's not the same as just printing hello world. Okay, even though in this case that monadic action is going off and doing I/O and talking to stuff, it's not observable. Okay, like you would observe it with increased CPU usage, and your data center would be hotter and things like that. Okay, so along with that, we can run those queries in a different order, for example. That doesn't directly stem from that rule, I think, but it's a thing. If you're just querying stuff, you can run stuff in different order. You could run them at the same time if you wanted to. Okay, but that doesn't work with monads. Okay, so monads, basically, if I've got two queries, I'm going to ask, what is your name, what is your quest, for example. I have to ask, what is your name, and wait for the answer, so that I can then throw it away and ask, what is your quest? Okay, monads force that to happen. Or maybe I want both the answers, but I'm going to stick them together at the end. So I can ask, what is your name? I need to wait for the value. Then I can ask, what is your quest? And get the answer. And then I'm going to put them together in this tuple at the end. I didn't need to know this x here. I'd never used it in this expression. So I could have somehow run these two queries at the same time. Okay. Monad doesn't let you do that. So what we need is applicative. And the interesting thing about Haskell is when you don't use it as a monad, when you use it as an applicative. So we have a couple of different formulations. This is the standard Haskell one, apply. And I like this one better personally. And they're equivalent to each other. And I've written out what they do in pseudocode here. So apply runs the left-hand side here, and then it's going to run the right-hand side as well, and then whatever's left-hand side needs to be a function, and it applies the function to the value. But you can see this f never gets passed to the right-hand side. Okay, so that's the big difference between this and bind in monads. That value is, you don't get to see any of the values of your actions until the very end. Okay. So that means we could swap these two lines around and you wouldn't be able to tell the difference. Okay. Not in the world in general, because if these were print statements, you would be able to tell. But in the case of a query monad, a reader monad, you can swap them around. It works syntactically because the variables are never used over here, and it doesn't matter which order you run queries in, or you can run them at the same time. Okay. And the other thing that the Haskell people drove is not Haskell itself, but it's fixing up the desugaring for do notation. So if you write a do expression like this in a recent GHC, it will desugar to applicative, not to a monad. Okay, and they wrote that so that their users can write do expressions, and it magically says, oh, we can run these queries in parallel where we want to. Okay, so if you turn on applicative do, it will desugar to a different lower level set of calls, and then because theoretically applicatives always work the same as monads, then you won't notice any difference apart from maybe some stuff can run in parallel in certain monads. Okay. Okay. So I find there's a paper about this, which I find really hard reading. I find all of Oleg's stuff really hard to read, but it's kind of interesting. So I'm not really going to explain how logic T does what it does, but I'm going to give you a motivating case for what we're trying to do. So I'm going to set up some numbers. I'm going to have all the positive numbers. I'm going to have all the negative numbers. And if I make a list of all the positives, 0, and the negatives, that's all the numbers, right? So now the numbers contains all the integers. And I'm going to say, all right, let's have a look for a number bigger than 100. So imagine this is a complex problem we're trying to solve and we're looking for a solution. but the solution we're looking for in this is there a number bigger than 100? Okay, so we're going to do this. We're going to say we're going to take the first result that we get out of this search, and our search proceeds as follows. We choose a number off the list. We say, is it bigger than 100? And if it is, we return it. Okay. And if we print a solution, there's our answer, 101. Okay. So do you see how that found this solution for us? Yep. Okay. Let's try a different query. Same setup. We're going to look for a number smaller than 0. Okay. What's a number smaller than 0? Well, if you look at this definition, you're going to tell me -1. Okay? Do you believe that? Why are you shaking your head?
No, I believe it. I believe it hangs.
Yeah, okay. If we run it, it hangs. Okay? What's going on? So this ++ operator is unfair in some sense. Okay? It gives preference to everything on the left before anything on the right. And because this list is infinite, we don't even look at any of these until we've gone over an infinite number of cases, which never happens. Okay, so it hangs. It's using CPU, diligently checking every single positive integer before it gets to try out 0 and the negatives. And that's why I constructed this list in such this weird way, so that I could get all the positives in there first before we have the other ones. Okay, that can arise just where you have big search trees. Like, it doesn't have to be the integers. It might be, all right, let's play a game of chess where we'll go off and move this piece and then just keep moving explore some really stupid branch of a game tree before backtracking and never actually getting to somewhere useful. Okay, so this is a very simple contrived search. So you can do something pretty simple to fix it with a list. Instead of using this unfair ++ operator, you can use interleave. So you can see down here what interleave is going to do. It's going to take one element from one list, one element from the other list, and one element from that list, and just go round robin between all the lists. Okay, so we will definitely eventually find a number less than 0 in that list, and instead of having to wait for infinity tries, we can find it on the second try, which is much better. Okay, there's nothing interestingly monadic there. Okay, interleave is a pretty simple function. I can imagine it being like an introductory homework kind of write this interleave function. Where it gets interesting is if you're trying to make a list transformer. So I want to say, here's an I/O computation that's going to produce a list of results. Here's another I/O computation that's going to produce a list of results. And I want to do some kind of stuff on all the results. You now sort of struggle to write the equivalent of ++ in a way that works for these infinite lists. So what am I going to do? Maybe run this I/O computation, which might run forever, and then run this other computation and concatenate the lists. Okay, so we'll never even reach this second statement if this runs forever. Okay, and so what logic T is an attempt to do that right. To say I've got two computations, and I'm going to say, all right, computation 1, run for a bit until you give me a result. And then I've got a result from you, and now I'm going to go to the other computation and ask you to run for a bit until you give me a result. And then I go back to the first one and say, oh, now you give me a result again. Yeah.
That sounds like something you could do with the conduit model.
Yeah, well, so I realised this afternoon, because they are phrased in such totally different ways, I realised, yeah, this afternoon they're really very similar. But the syntax, if you read the Logic T paper, it looks nothing like conduit, but actually it is very similar indeed. And it's sort of running two sinks, and two sources, sorry, and saying, yeah, you run until you yield, now you run until you yield, now you run until you yield. and I'm going to yield results from the two of you.
You could do that in your conduit one. I thought that was the way.
I only realised how similar they were about 2 hours ago, as I was thinking about how this actually worked. So maybe I'll have a play with it.
Seeing some multiple
Yeah,
sources.
yeah, and there are loads of conduit combinators for doing things, so you might end up with something very similar to this. Yeah. Okay. Okay, so free monads, we've seen these already, it turns out, several days ago on the set monads. So, if you click the hyperlink that takes you back to the set post that I would have wrote, we've got this set thing which is sort of describing how to construct a set. It isn't a set, it's a set of monadic, it's a data structure that captures how to build a set. And then we have an interpret function here which we can run with constraints that says for certain kinds of certain instructions that know how to build a set, we know how to interpret those into a real set. Okay, and it's basically making a monad. So we've got return and bind that don't have any constraints, and then some special stuff, which in this case is prim for primitive sets. Okay, but we could use this technique for lots of different things. So we could keep return and bind and plug in whatever special application specific things we want. Okay, so here we've plugged in some set stuff and a set interpreter, but we can put something else in. So there's a package control monad free, where the special stuff is a data type that needs to be a functor, and then there's a freer monad which it doesn't even need to be a functor, and it looks sort of like this. So we've got a free monad that says you can either return a pure value or you can do this bind between our data type, our special stuff here, and the rest of the program. Okay, so I probably should have renamed these. This is return and this is bind. Okay, and then this F is where we plug in whatever our special stuff is. So for sets, we would just have one constructor here that is the primitive constructor that we had before. Okay, and so instead of defining a set in the way we did before, we can say it's a free monad where the special behavior is what you get from set FF. Okay, so that captures this style of building up a syntax tree that all it's doing is kind of copying in your monad notation into a data structure and then saying, well, someone else has got to interpret this later on. Okay, yeah.
Is that supposed to be F3, the last one, or just?
Oh yeah, that should be F3. Yeah, yeah. Okay. So the F3 is giving us the monad structure as turning monads into a data structure, and the F here is giving us whatever is specialized to what we want to do. Okay, that's right. And there's plenty of talks about why you should use free monads and stuff. And okay, so day number 10, related to the free monads, is modular interpreters and extensible effects. So I'm going to talk about open unions first and then show you how those fit in. So we've got this union data type here, either string or integer. So that can be either a string or an integer. Okay, if you give me a string, I'll give it a type alias x. If you give me a string, I can give you an x. And if you give me an integer, I can also give you an x. Okay, and I can project out. If you give me an x, maybe I can give you back a string. If you give me an x, maybe I can give you back an integer. Okay, so you can sort of forget this constructor here. Just pretend that you've got this opaque type x that you can inject strings and integers into and maybe get them back out again. Okay. But using advanced type level technology, you can make these open unions that you don't have to specify in your data type ahead of time what those possible member types can be. Okay, so you can define a type like this: union, foobar, baz. These are types, and I can inject in to a value of this type, which looks a bit weird because it's got a list in it, even though it's a type signature. If you give me a foo, I can give you a value of this type. If you give me a bar, I can give you a value of this type. If you give me a baz, I can give you a value of this type. Okay, so whatever type you give me, if it's in this list, I can give you a value of that union type. Okay, and maybe I can project them back out again if they exist. So that's why I had stuff that looks a bit like this. We've got injections and projections, and here we have a single injection function and a single projection function. So if I do that, I make a free monad where the special filling can be a list of lots of different data types. Okay, so what you can do there is say, well, this is a list of different kinds of effects. So maybe I want to have a computation which can do a reader monad style read and also output a line to standard out. Rather than having to make a single free monad data structure that knows how to do reader stuff and outputting a line, I can make two different data structures. One that says, here's the effects for printing, and here's the effects for doing reader stuff, and then I can compose them together by sticking them in. I could say free union read comma print or something like that. Okay, you kind of had to see an example of that to make sense, and I don't have one in this talk. Okay, but that means you can build up a syntax tree that looks like a monadic bind, but the actions in there can be all kinds of stuff, and that can change based on the type signature. So when you've done that, because it's a free monad, you've got to have an interpreter for it, and you aren't going to get an interpreter that can interpret every single type. Okay, I've said you can stick anything in there at compile time. You're not going to get an interpreter that can understand all of those. So what you need is something like an extensible modular interpreter, and the extensible effects package lets you build those. So I can have a free monad with a list of different effects I can run, and I can say, here's a module that knows how to do reading, here's a module that knows how to do printing, maybe here's a module that knows how to do non-deterministic choice, and I can stick those modules together, and I will end up with this interpreter that knows how to handle all of the effects that I've used in my type signature. Yeah. It sounds pretty good on paper. It's I did a talk earlier this year on actually trying to use this for a small project, and I managed to get GHC to give internal errors, and this shouldn't be happening, and oh my god, report this compiler bug. And it had, very similar to lenses, it had the same kind of problems where the type errors just looked totally weird. So it was very hard going. I found it very enlightening to do, but I'm not sure I'd recommend it to anyone to actually try using in real life. But it's pretty interesting. Like, it's an interesting technique to say, I'm going to do a free monad, but you can stick anything in it. Okay. 2 more days left. This is one that it turns out to be impossible to implement, or some such similar statement. And that's doing sort of type-safe dynamic types. So we want to do stuff with dynamic types, but we want some kind of compile time verification that we aren't going to get a runtime error. Okay. So if we have a look at what dynamic types from data.dynamic look like in Haskell, you've got this type called dynamic, and if you give me a value that's got the typeable constraint, so almost any value, I can inject it into dynamic. Okay, and if you give me a dynamic, I can project out that value maybe, or if it's of the wrong type, it'll return nothing. So if I take an integer, inject it into dynamic, and then try and project out a string, what I'll get back here is nothing. Okay, so that looks really like the injections of the open unions of the day before. Okay, so it's type safe in the sense that you're not going to make your program crash, but there's no compile time checking that lets you say, well, I know that I've put an integer in here, and so I would like the compiler to tell me if I try and pull out a string. Okay, all you get from the compiler is to know, yeah, maybe you'll get back a string, or you might get back nothing. Okay. So here's some dynamic typing stuff that happens in Haskell. We've got the IO monad and a generalization, the ST monad. So I can make an IO reference, which is going to store a value of whatever. So I'm going to store an integer, for example. And what I get back is an IO ref value that in its type says this is a reference to storing an integer. Okay, so I can read it, and what I get back is that value. That's checked at compile time. So if I make an IO ref pointing to an integer, the compiler checks that when I read it, I'm treating it like an integer. Okay, I can make a different kind of IO ref with a string, and the compiler will check that's a string. And then the ST monad generalizes that in this way that turns out to be pure. You can run something in ST and you get back just the pure value at the end of the computation. So it looks quite imperative, but it isn't doing anything it's not doing any IO. Okay, so these type signatures are just the same as the IO ref ones in a different monad. They have this little S in here, which is a phantom type to make sure that you don't run two different computations and share a reference from one to the other, which is a little subtlety, but you can mostly ignore it. How could we implement this then? Well, this is what the source code for the library says in base. It refers to ghc.magic. All right, well, that's a bit lame. So I came across this the other week. The key monad, it still needs a magic implementation, but it needs a less magic. Okay, not as much magic. So it's interesting in that sense. And one of the points of the paper that talks about this is that because it needs less magic, it might actually be more helpful in trying to do some proofs about the ST monad. So what this monad gives us is a function called new key, which is a bit like new stref. It'll give us a key that has a type associated with it. And all we can do with this key is it doesn't reference a storage location, so it's different from a stref in that sense. It's just a name with a compile time type attached to it. Okay, it's some identifier, and we know that this is maybe a key to an integer. Okay, all we can do with it is this. We've got one function. We can take two keys and we can compare them, and if they are the same key, we get back, instead of true or false, a sort of dependent type version of true or false, which is we either get back nothing if they're different, or if they are the same, we get back this data structure, which tells the type checker at compile time that A and B are the same. Okay, which is slightly weird, but it's what happens. Okay, so we can do a case match on test equality, which I'll show you here. So one building block, simple building block, is you can make a thing called a box, and it can store a value of type A, but the type for box doesn't have that type. So it's a box. We've got no idea what's stored inside it. Okay? And I can have a key, which does have a type, and I can come to the box and say, does this key unlock this box? And it will either work and give me the value back, or it won't and give me back nothing. Okay, that is very much like the toDynamic from dynamic stuff, except we've got this key in there. And what the key means is that the compiler knows at compile time that the type of the key matches up with the type of the value in the box. Okay. So we can do strefs this way. What you do is, a new stref is just a key. We use that key in a lookup table. The lookup table maps keys to boxes, and then we come along and I want to read an stref. Well, I go to the lookup table and I just try and unlock every box, and hopefully one of them will get unlocked, and that's the value of our stref, and we know it's the right type because it's the type that is the type of the key, the type stored in the key. Okay, it's this weird interplay of stuff happening at compile time, where we're saying these types are equal at compile time, and stuff happening at runtime. You've probably come across it in Idris, I would guess. Dear Idris fanatics. Okay, so there's some other stuff you can do. So stref was all about references. There's other stuff you can do where it's useful to have some kind of identifier at runtime with a compile time type attached to it. So in their paper they talk about doing arrow notation, but using do notation rather than special arrow syntax. So the thing with arrows is you don't get access to the values in between arrows at inside your arrow code. Okay, the arrows get stuck together and can pass values between them. So that works out well here. You can have a key that is a sort of proxy for where the values are passing, but you can't ever get at that value. What was the other one? Syntax tree stuff, where you maybe embed a programming language as a data structure tree, and you want to have variables and identify a variable, but then you want to put a type signature on that variable and have the compiler checking that you're only using those variables in the right place. So it brings in some interesting stuff that doesn't initially look at all like strefs. Okay, last day, might finish just about at the right time, are continuations. So continuations are very difficult to understand, and I advise you to never use them, ever, especially with what else you can do in Haskell already. But a continuation is a value that represents the rest of the program to be run, okay? Which is what you get from monads already, sort of, okay? So we already have, we're going to do a thing, and then we're going to do the rest of the program, okay? What the continuation monad does is lets you get at this inside your monadic code, okay? So this is a great type signature. Call with current continuation. So if you run some code with call cc, and here's a function which has got that type signature, or this type signature, that function gets passed a continuation for the rest of the program, okay? And so inside that function, we can call the continuation, and it will act as if we had just returned from call cc. Okay. So there's a few examples. Here's an example. So this trace is just a lifted print that I did. So we're doing a continuation transformed over IO. Ignore these bits. I can't even remember what that one is. And we're going to have this program. It's going to print a thing. It's going to call function B with with current continuation, and it's going to print function B return the return value. Okay, so that will print the value that this returns. Okay, what's this going to return? Well, normally, if that wasn't here, it would be the value that comes out of the end of function B. Okay, what actually happens with function b is there's the continuation going in as our parameter. We say function b inside, and then we invoke the continuation with the value 7. Then we are allegedly going to print part 2 and finally return the value 10. What comes out is we go inside we start, we go inside function b, and then suddenly func b returned 7. Okay, we've invoked this continuation, it's aborted the rest of the program. Okay, and sort of popped back out here. Okay, this is the most amazing way to get completely tangled in any reasoning about the flow of your program at all, because it turns out you can pass this continuation down into another function, and this function all the way down the stack can pop back out here by invoking the continuation. Okay, you can do things like store that continuation in a data structure and invoke it 100 times, and suddenly the rest of your program will run 100 times. And then you're like, what? Yeah. So it's not actually that different from what monads do, because monads do have this continuation at every bind. It is the rest of the program. But this lets you, inside your monadic code, get that as a value and do crazy stuff with it. Don't do it. Things you can do with it, like maybe you could implement coroutines. So the yield operator and the await operator in conduit, that is saying, all right, when you call await, take the rest of the program, stash it away somewhere, and then go and do this other stuff. And then when I do yield says, all right, stash this away somewhere and go and call the continuation over here to come back from await to carry on running that until we call await again, at which point we stash that away and come back to this continuation to carry on running this bit. Okay, so all kinds of crazy stuff. In practice, probably it's better writing a monad. Some people would probably advocate doing a free monad if you're getting anywhere in that direction. Probably to do stuff just with continuations is if you want to write an impenetrable paper, such as the Logic T paper, which has a lot of continuations in it.
You're describing delimited continuations and so on?
This is just normal. Well, it's delimited up to this run cont, but no, not delimited. Okay, that's the end. That's my 12 days of Haskell.